we will have to invite the next speaker on stage who will talk about challenges of deep learning application in surface inspection. We have Fernando Schneider. Welcome. So you also have a pointer here in case you want to point.
Yep.
This was the...
OK, thank you. So hello, good morning, ladies and gentlemen, and welcome, dear guests, to my presentation, Challenges of Deep Learning Application in Surface Inspection. My name is Fernando, and I'm leading the hardware and software sales at SAC. So my goal is to make the next 15 minutes as impressive and informative as possible. So first, I will give a definition of deep learning-based systems, its challenges and opportunities. Then I will give an overview about visual 2D surface inspection and its challenges. Finally, I would like to talk from an expert point of view about experiences so far applying deep learning methods in surface inspection. See how they support inline machine vision application in industrial production. So for those of you who don't know the Sirius advanced cybernetics company, here are just some quick facts. Currently, 40 employees at our location in Karlsruhe, about 1 hour to the west from here. We have been dealing with machine vision technology since 1996. Worldwide, we already integrated more than 10,000 applications with focus on our core competences, surface inspection, and inline 3D inspection. SAC combines 3 business units. Hardware, so we manufacture our own patented transistor systems for perfect surface inspection. Software, we develop our own machine vision operation environment, Coke 7. And our application center is integrating turnkey vision solutions in industrial production. So our customers benefit from this combination. Let's come to the first part of my talk, deep learning in a nutshell. As a subtopic of artificial intelligence, machine learning, I would like to give a quick overview of deep learning. Compared to simple neural networks, machine learning algorithms work with multiple hidden layers to progressively extract higher-level features from raw input data. Training of neural networks requires a huge amount of labeled data. Optimization at each training step improves the metric to find the best mapping of input data to output data. And finally, the trained model is applied to not yet known, unknown new input data. Now let's have a look to the difference between conventional image processing and deep learning-based image processing. In conventional image processing, a software engineer first develops various algorithms. These are processed by an image processing application engineer into many different individual programs. The individual programs are applied to new input data, so in our case, images, and produce a result. So if all the engineers have worked correctly, even the result is correctly. The process of deep learning-based systems is different. A lot of image data must first be collected, labeled, and sometimes annotated. Then computations and experimental deep learning model development is important to find and validate the optimal training or the best training model for the desired use case. Finally, input parameters, so images, are passed to the trained model for evaluation, and we get a result. But in this case, it's really hard, to almost impossible, to find the way how the result came. So yeah, you can say you have just to trust the trained model. This will lead into the following challenges, especially for industrial applications. A large amount of labeled data is required for an efficient training. This consumes a lot of time and manpower, as we heard before with the previous speaker. Was good. So the application to unseen data must work in a process and reliable way. Process safe, yeah. Fluctuations in production, different operating environments and conditions, such as ambient light and so on, must be taken into consideration. So there are many different methods to build and combine neural networks. Nevertheless, there is no general strategy to efficiently select, train, and validate these models. Finding and training the perfect model is like an experiment with an uncertain outcome. Training and experimentation requires a huge amount of computation. High-performance hardware is needed, which means more acquisition costs. And even bigger problem, in my opinion, is the time loss during or due to applications in the industrial environment, which are have a fast cycle time. So we need fast algorithms. So we can say, summarized, the implementation of deep learning algorithms in machine vision are still often limited by the major challenges. Now you may ask, why the hell there is such a hype about deep learning? Where will you look? Artificial intelligence, deep learning are dominant topics of our time, even in machine vision. So the main benefits can also be quickly summarized. Less general programming effort, especially when dealing with a large number of different tasks. Complex problems such as image classification can be solved with seemingly little effort. And an aspect that is often underestimated, in my opinion, shifting of engineering services. That means deep learning could be translated into programming by showing. So the responsibility of machine vision solutions can be shifted from expensive machine vision engineers to cheap technicians. On top, the specialists, the technicians, are usually more familiar with the special features of the inspected parts. So now we come to the visual 2D surface inspection, a topic you might be familiar with, but not always trivial in terms of challenges. The definition, the aim of surface inspection is an objective and reproducible evaluation of deviations of the surface with regard to component tolerances. Do you know the ISO standard 8758? When I started at SAC, a colleague told me, surface inspection is the Champions League of machine vision. So if you also want to play there, you have to read the ISO standard 8758. And I did. All the different defect categories are listed and defined there. You will also find the definition of typical surface defects, such as scratches, dents, deformations, and so on. So I don't want to bore you with all the other listed defects, but all of them have one common feature. Depending on the material, surface texture, and size, the defects are very challenging in visual 2D surface inspection. So on the right side, you see a wave washer, shiny, glossy, and I'm pretty sure that you can clearly tell me where are the defects on this part. Don't you? I guess not. So let me now explain how the application of deep learning models help in challenging surface inspections. The key is the combination of deep learning algorithms with conventional image processing. An efficient training of stable deep learning models is mainly achieved by these points: reducing the complexity of models and model architectures. This is done by pre-processing the data with conventional image processing. For example, compensation of positions. Deep learning models are relieved by conventional processing of image data, for example, the reduction of image size, cropping of relevant areas, and so on. This allows a faster training with less training effort, better inspection performance, and higher confidence. But one of the most important requirements for an efficient training of stable and reliable deep learning models are improved images. Those you get, for example, from our patented Tristor sensors. The normalized image data significantly increases the stability and reliability of trained models and their application. So I brought a part. It's a pressure sensor, high reflective, and normally it's horrible for every application engineer to detect any defects. And with Tristor normalized data, which you see here on the slide, you see the smallest defects even of this horrible part. So this is what we need to train the models. We need optimum and best image data, input data. So now we know how to build neural networks, and then we will show you how easy and reliable implementation and application of neural networks could be. The mentioned efficient training on the previous slide with optimized image data enables fast validation and implementation. Modern vision operation environments offer a clear and easy way to annotate image data, train, validate, and embed deep learning models into conventional solutions. Post-processing and additional reliable validation of the results using conventional vision methods should also be easy and efficient. Now, surprise, surprise, Coke 7 from SAC offers all these possibilities. The smart surface inspection in Coke 7 combines perfect image data with optimally matched neural networks. All sensors of the Tristor sensor family are seamlessly integrated. Deep learning, or combining deep learning with Tristor optimized image data, enables to solve complex surface inspections with Coke 7. Quick, efficient, and reliable. Our vision operation environment also offers different network architectures for less demanding applications or tasks. So you can simply and conveniently train and validate neural networks in our free demo version or in the Coke standard license at no extra charge. That's our philosophy. So it's a free and easy way to evaluate if you are creating real added value by using deep learning technology. And we will be happy for a personal live demonstration at our booth in the Hall 10 and booth D14. That's it. Thank you for your attention, and I'm happy to answer your questions.
Thanks. Thanks, Fernando. Really interesting. Do we have questions from the house? Even if it's not for Tristor, if you guys are not interested, or if you're interested, please go ahead. Otherwise, I have a few.
Okay.
So you said that you're using a trained model, right? So Tristor is using a trained model, and it is a patented.
Tristor is a sensor, so we get the best image data of challenging parts like reflective or black and black. So we get the input data, the images from Tristor, and they are we use these training data with normalized data to train the models.
So Tristor is a sensor.
Yes.
Okay. And where is your trained model living there? It's a software that accompanies the sensor, or?
Yes, it's our own software which we developed, and the models are they're model. Let me see. yeah, it's not just one model, though we have different models, but optimized for surface inspection. What is our passion?
Okay, so for example, let's say your customer is an automotive company. I'm not naming names here, just as an example. And you have different automotive companies manufacturing cars, and that's a typical, very common. I mean, I have seen surface inspecting robots with vision system inspecting the car bodies and all of that. So the provocative question here is, can you use the images from one manufacturer to train your model, and then you have a trained model? Can you use this trained model from an ethical point of view to solve a similar problem for another customer?
That's a good question. I'm not too sure, but we can talk later on at our booth with our technician who's here today. And yeah, I'm not sure.
Is there where I'm coming at, is there a specific NDA that you're going on? I'm sure there would be NDAs with your customers.
More than 95%, yeah.
Yeah, so they would say you're not allowed to use my data.
That's why they train the models on their own PC. They have their own GPU where they train their models. So yeah, they do it internal. And we work with partners and customers, but also with a lot of integrators who are using our technology. And yeah, that's it.
So you cannot really use the trained model for one. I mean, when you have an NDA, you cannot use the trained model that you have developed with one customer to use. Not just. I'm not saying that you're using their images. No. I'm talking about the trained model, because once the model gets trained, you don't use the images anymore, because the model knows what is good, what is bad, what is. For example, you mentioned the ISO specification, and then you can also use to classify the defects as well, right?
Yes, of course.
So this is what I mean.
Yeah.
So that's
the most important task.
That might have been another challenge, right?
Yeah.
Okay. So I don't want to hold you longer. I cannot hold you longer enough.